Okay, recording has started. So I do have a question here from Carnegie Johnson was asking about the YouTube URL. So all of the videos that I was showing before, all of those are available on the Zyxel America YouTube page. So just go to YouTube. I think the page is called Zyxel America Service Provider. Just put in Zyxel America, you should be able to find it, and all the videos are there. So without further ado, we'll go ahead and get started with today's presentation. We'll start with a very brief overview of who Zyxel is in case you're new to the family. So we've been making computer networking equipment now for 30 years. So we got started back in 1989. Started off making analog modems back in the day. At this point, we've got over 100 million devices deployed out in the field, and we are serving 150 different global markets. Our U.S. office is located in Anaheim, California, so that's our warehouse, that's our sales and marketing, that's also our tech support. So if you call in needing help for tech support, you are talking to an actual Zyxel employee in the actual Zyxel headquarters here. It's not farmed out to a third-party contractor. It's not farmed out overseas. So that's it as far as just a brief background, and we'll start talking now about wireless. So I want to talk about a couple of the different players you'll see out there. You'll see these mentioned a lot. One is IEEE. So IEEE is a working group that creates standards for all sorts of stuff. We're mostly focused on 802.11, whether it's 802.11a, b, g, n. These are standards that are put together by these working groups. These working groups are a collection of engineers, chipset manufacturers, hardware manufacturers that try to create a standard to define how the technology works. The Wi-Fi Alliance is a separate group. They're the guys behind the Wi-Fi certified logo, and they're the ones that have recently rebranded 802.11ax as Wi-Fi 6, 802.11ac as Wi-Fi 5, etc. So they're more of a consumer-focused group, and what they try to do is they try to enforce compatibility between different vendors' product. Despite all the time and effort that goes into those IEEE standards, there's still different ways of interpreting those standards, and there are still holes or lack of detail in certain aspects of that standard. So the Wi-Fi Alliance is there to try to help patch those holes and make sure everybody that sells a device that's a Wi-Fi device can talk to all the other Wi-Fi devices that are out there. And then on top of all that is the government agency, the FCC. Those guys set the rules for which RF spectrum can be used, power output, and other behaviors of RF devices. So that's enforced via law, although they don't do quite as much testing and enforcement as most people might think. So let's talk a little bit about radio waves. When we're talking about radio waves, this is the same technology that's being used, for an actual radio. It's used in cordless phones and other devices, things like that. A good way to think about radio waves is to think of them as being similar to sound waves. And as we go further into this, I'll come back to that. But that's a good way or a good analogy of thinking about it. So some things to know is as frequency goes up, you can encode more data on those waves. Frequency goes down, less data. Also, as frequency goes up, the less range you're going to get on those devices. So a good example for those of you that are as old as me, so those of you that are at least maybe in your late 30s, is cordless phones. You might remember the original giant cordless phone that you had as a kid. That thing worked great, right? Get on that cordless phone, you could walk out onto your yard, maybe even walk halfway down the block, go over to your friend's house, and be able to still maintain a phone conversation. Those were the days of 900 megahertz phones. So in order to improve sound and deal with some interference issues, what we saw in the 90s was a move to 2.4 gigahertz phones. So those phones advertised heavily the fact that they had better sound quality, but you quickly learned that you could no longer walk down the block. Maybe you could use it out in your yard, maybe not, depending on how your house is constructed. And then towards the end of the 90s, you saw a move to 5 gigahertz phones for your cordless phones in your house. Same thing, pitch The idea that you get much, much better sound quality, better security, all of which is true because you can fit more data on those waves, but the range got even worse, and you ended up in situations where maybe you had to put repeaters around your house. So it's the same thing. Those are the same frequencies being used by Wi-Fi, have the same sort of issues. So when it comes to sending data, generally when you're using radio waves, you have to have a license of some sort to be able to use those radio waves. So if you're a radio station, you have a license to be able to broadcast on whichever radio station channel you're using. For some of the outdoor point-to-point and other sort of outdoor solutions, again, you need to have a license. Your cellular phones, you generally need to have a license. So there are some chunks that are open up that anybody can use. So we abbreviate those as the 900 megahertz spectrum, the 2.4, and the 5 gigahertz spectrums. So generally, there's never been anything that's data related really on the 900 megahertz frequency because you just can't fit enough data on there. 2.4 is where Wi-Fi first sort of jumped in with 802.11, then 802.11b, and then 5 gigahertz was used for 802.11a, and then started to be used for 11n and 11ac pretty much as the standard and the go-to because they're much faster because of higher frequency. So when we're talking about radio waves here, we like to talk about power. Power is a good rough measurement to give you an idea of the sort of coverage area you might have. So a lot of people like to use watts or milliwatts as a way of measuring power. Generally, from a professional standard, when you're looking at spec sheets, you'll instead see something called dBm, decibel milliwatts. So dBm is generally a better way to go. It gives you a much better approximation of the relative coverage area as you increase power. It also makes it easier for you to add any sort of antenna gain or bonus that you're going to get or amplification to the output power of the chip itself. So as a general rule, for every 3 dm you increase the power, you are doubling the output power. So 20 dBm is 100 milliwatts, 23 dBm is 200 milliwatts of output power. So it makes it sound like, if you're just looking at milliwatts, you'd go, wow, I've doubled my coverage area. I've got twice the power, the signal can go twice as far. And really, calculating distance over free air is kind of a nasty sort of logarithmic function you need to calculate. But it's kind of, just for an easy to understand, it's kind of like an inverse square rule. So as you go from 100 to 200, the increase isn't actually that much as far as coverage area goes. So going from 20 to 23 dBm is a much better approximation in your head as to how much bonus area or bonus coverage you're going to get. The other things that we're looking at here is something called signal-to-noise ratio. This is going to be key when it comes to speed and when it comes to those edge case issues. So that's basically how strong is the signal that the Wi-Fi devices are wanting to listen to versus the signals of other things that you don't want to be listening to, whether it's other access points at your neighbor's house that's using the same channel, whether it's Bluetooth devices, whether it's just RF noise in general that might be in the environment. So signal-to-noise ratio is something that's going to be key for you there. And then another term that we use a lot here is attenuation. So attenuation is basically how we describe the signal strength degrading, whether it's just based on distance and open air, or whether it's from obstructions that absorb the signal itself. So to give you some examples here, up at the top there, you'll see a nice logarithmic formula. That is telling you how much distance you're going to get with RF signal, assuming there are no obstructions. It's just traveling through free air. As you can see, it's kind of a pain to try to calculate. And of course, nowhere in the real world do you have a situation where you've just got clean open air, no physical obstructions, no RF interference or things like that. So then we've got some just references here as things that might degrade the performance or attenuate that signal. So a standard window is going to give you about 3 dB degradation or attenuation of that signal. So it's going to cut your signal in half. Remember, 3 dB is essentially doubling the power, so subtracting 3 dB from your signal strength is essentially cutting the signal strength in half. Tinted windows, where you've got something that's been put on there to help keep the heat out or keep the UV radiation out, that can give you up to 8 dB loss. And then walls can be anywhere from 10 to 20 dB of loss, depending on what those walls are made out of, whether it's just simple empty drywall, or whether we're talking concrete or something that's got pipes and wires in it. So just some stuff to keep in mind when it comes to planning coverage area and understanding where that signal is going to go as it comes out of your Wi-Fi device, whether an access point or a phone or a tablet. So when we're talking about Wi-Fi range, we're looking at a combination of signal strength, the signal-to-noise ratio, attenuation, and the frequency that's being used. Another thing that people tend to overlook is that there's a huge difference in power output between a traditional business class access point and your client device. So, an access point easily 500 milliwatts of power. And I know I said we should use dBm, but for this one I'm using milliwatts. So you've got 500 milliwatts of power, but your iPhone is maybe somewhere in the 8 to 25 milliwatts of power. So you can see there is a huge difference in the power output, and that's going to be the deciding factor as far as your range goes. It doesn't matter how far the access point can send its signal if it can't hear the devices that it's talking to, because Wi-Fi communication is a two-way communication. So we've got a question here from Nicholas, really quick. Was asking, what device or software can we use to find the signal-to-noise ratio? Look for a spectrum analyzer tool. There's lots of them out there for free or for cheap for Android or iOS. Those will generally have a setting in there that will show you your signal-to-noise ratio. Wi-Fi adapters in laptops used to have such tools, but these days I haven't seen it. Doesn't mean they're not out there, but the built-in Windows signal strength tool doesn't really show you that. There are some dedicated software you can go out there and buy or download that will help show you that signal-to-noise ratio. And there are special devices or USB dongles you can buy called spectral analyzers that will provide the most accurate breakdown of what's going on in the RF spectrum where you're at. So anyway, back to Wi-Fi range. So that's something to keep in mind here is when you're planning your coverage is what is the weakest device that needs to be communicating with your access point. That's going to be the limiting factor for coverage, not the access point. The other trade-off here is because that access point signal is going really far, but the client devices aren't, you end up in situations where your access point is causing interference to other access points, whether in the same office or in a next door office or in a building. We run into this a lot where the access points have the power cranked up much higher than they need to be for the coverage that they're providing, and they end up causing interference with each other and degrading the overall performance of the network. And we'll talk a little bit more about why that is in a little bit. Some other things to keep in mind here is RF behavior. So again, if we go back to sort of like the analogy of thinking about Wi-Fi as sound waves, it's the same sort of thing. It's the difference between going into a concert hall and having a conversation in an empty warehouse. You get situations here where the RF can be attenuated, as we talked about, as it passes through obstructions in the environment, whether that's people or walls or industrial equipment. It can scatter as it bounces off of things, so it can take what's a single beam and sort of break it up into 3 lower powered beams, carrying the same information. You can get reflections. I'm sure you've dealt with this where you're outside somewhere and because the sound's reflecting off a wall, it sounds like it's coming from a different direction other than the sound actually is. So these are all things that we have to deal with in the RF environment that can be causing issues. So the signal may be strong. You may not have anything blocking that signal, but you may end up in a situation where the signal is bouncing off of different objects. So now you've got what would be the sound equivalent of echoes, which are making it hard for your computer device to be able to understand which is the information it needs, which versus what is an echo that can be ignored. Okay, one more issue we run into here is when we were first creating 802.11, they never imagined that you'd have so many devices using the network and that there would be so much what I'm going to call streaming type data that's being sent consistently. So there wasn't a lot of plans to deal with a crowded environment. So with RF, only one device can transmit at a time. So everybody is taking turns broadcasting their data. The access point sends some data to a client. The client then sends some data back. Another client device may want to send some data to the access point. And what happens is if each of those devices broadcasts at the same time, it creates static or creates noise. Again, it's like being in a crowded room and you've got multiple people talking to you at the same time. It can be really hard to figure out which one person should I be listening to and to make out what they're saying versus the other person who's simultaneously trying to talk to you. So the way this was originally dealt with in 802.11, and it doesn't matter whether we're talking 802.11a or 802.11ac, it's the same thing, is basically the device listens to see if anybody else is talking. If nobody is talking, then it goes to and transmits its data. If somebody is talking or transmitting, it will then back off for a random period of time and then repeat the process again. It works fine in in an environment where you don't have a lot of client devices, or where you're doing spotty type traffic, such as web browsing, where you only need to send data for a second or two and then nothing goes on. So you don't get a lot of people stepping over each other. But with VoIP traffic and video streaming and file transfers, or just in a crowded environment where you've got a lot of clients, what happens is two or more devices will stop, they'll listen, they'll say no one's talking, so two or more devices will then talk at the same time, thereby interfering with each other. The other problem we run into related to this is something called a hidden node problem. So the blue circle there, or ellipsis, that's the range of the access point. So it can hear everybody that's in that blue circle. The problem is your client devices, which are lower powered, have generally smaller, weaker antennas. They might be on opposite sides of that ellipsis, and they're not able to see that the other guy is transmitting data. So they'll think everything is clear and they'll decide to transmit. So you end up in a situation where you've got two devices transmitting at the same time, and your access point is unable to make out who to talk, who they should be listening to. So you end up in dropped packets. So again, this is something else that goes on quite frequently, even in low density deployments out there. Okay, and then lastly, I want to talk a little bit about data rate versus throughput. These terms are used a lot, they're thrown around a lot, and people can use them to mean different things. So for the sake of our conversation today, data rate is the maximum amount of data that's transmitted between two wireless devices. So you'll also see this being called a physical rate or a link rate. What's key here is this includes not only the data, say the file you want to send from one device to another, it includes all of the protocol overhead. When we're dealing with Ethernet, there's not a lot of protocol overhead. Ethernet's pretty much, 99% of the wire speed is the amount of data you're able to transmit. With Wi-Fi, because we're operating in RF, where there's all sorts of other forms of interference, environmental issues might degrade performance or cause packets to be dropped or lost, there is a ton of protocol overhead that doesn't exist in Ethernet. So because of that, you end up with lower throughput. So in throughput being, say for instance, if you go to speedtest.net and do a speed test, that's what I mean by the throughput. So it's only measuring the data that's going from your laptop, say for instance, to the speed.net servers. It doesn't include all the extra protocol that your laptop is adding in that makes Wi-Fi possible. So because of that, you're going to see a difference between the rated speed or the data rate or the physical link rate that you see advertised on wireless products versus the throughput that something like speedtest.net or iPerf or something like that will show you as being the amount of data you can transfer from two locations. So generally with Wi-Fi, it's somewhere in the ballpark of 40 to 60% of the physical link rate that you currently have achieved is your throughput. So just something else to keep in mind. You know, I would much prefer we use throughput when we advertise speeds of our wireless products. Unfortunately, there's no standard out there as far as protocol on the types of data, whereas there are standards for the physical link rate, and the physical link rate is what determines compatibility between devices. So unfortunately, the Wi-Fi world is focused on the data rate when it comes to advertising products, you know, N300, AC 2600, things like that. Those are all based around the data rate, not the actual throughput you can put through them. Okay, now I want to move forward and talk about how do you increase speed. So when it comes to the Wi-Fi protocols, there's a couple different strategies that are used to increase speed. One of them is increasing the encoding. So going from 64 QAM to say 256 QAM on 11AC, or jumping up to 1024 QAM with the new 802.11ax. We can also increase spatial streams, and we'll talk a little bit more about what those are, and then increasing bandwidth. So for instance, 802.11g used 20 megahertz bandwidth per channel of operation. 802.11n jumped up to 40 megahertz, effectively doubling the speed by using twice as much of available RF bandwidth. 802.11ac gives you up to 160 megahertz of bandwidth that you can use at a time. So let's start talking about channels and bandwidth. So we're going to start by talking about the 2.4 gigahertz spectrum. The 2.4 gigahertz spectrum in North America is roughly 60 megahertz of available usable channel that we can broadcast on. So you might remember that I just mentioned that each channel in 802.11g is 20 megahertz. So each of the different channels that you will see when you go in to choose a channel, 1, 2, 3, 4, etc., actually overlap with each other because those channels are much smaller in their range. So in reality, using 20 megahertz channels, you've only got 3 channels to choose from before you start causing interference between your RF devices. And again, 2.4 is shared by all sorts of stuff: digital cameras, smart home appliances, Bluetooth, video game controllers, wireless headsets, etc., etc. So one of the ways they went to increase speed from 11G to 11N was to go from 20 megahertz channels to 40 megahertz channels, which is great, but again, you've only got 60 megahertz available. So you can't have 2 different devices operating on 40 megahertz channels without causing interference. So obviously this creates issues if you're doing an office or a large home or a hotel where you've got multiple access points. You're either going to be operating on the 40 megahertz channel and causing interference with each other, which degrades overall performance, or you're going to have to scale them back to 20 megahertz channels. So you're never able to achieve, in theory, that maximum speed, and they're essentially by default cutting your bandwidth in half. So that's one of the big reasons why with 11AC and then the tail end of 11N, you saw a big push to using 5 gigahertz. So you can see here when you go to 5 gigahertz, there's a lot more spectrum available. I think there's 26 channels, I think that's right, that are available to choose from if you're using a 20 megahertz channel without causing interference. So it makes it great for high-density deployments where you've got a lot of access points in the area because you get a lot of channels that aren't going to cause interference. So that's one of the big reasons we saw a push to 5 gigahertz, in addition to the fact that you can have higher encoding and fit more data onto those higher frequencies. Now you'll notice though we've got some different color coding going on. So a big chunk of those available channels are in that little orange area there. It says DFS channels. So what are DFS channels? So that 5 gigahertz spectrum is shared not only for RF devices, but it's shared with weather radar, airport radar, things like that. So if you see something that's called DFS, that's telling you uses something called dynamic frequency selection. Basically, your access point has to monitor the RF spectrum, and if it detects radar in operation, it essentially shuts off that channel for a certain period of time. I think it's a minimum of around 30 minutes or so. You have to allow the radar to operate. And so if you're in an area where you're nearby an airport, where they might be doing that, or nearby a weather radar or a military base, those DFS channels might be going offline a lot of the time. In addition, the certification process for RF equipment to operate in those DFS channels takes a long time. I'm not sure what it is today, but as of a couple of years ago, it was taking 6 months extra just to get certified to be able to operate on those channels versus the normal FCC certification. So because of that, a lot of consumer equipment doesn't support the DFS channels. So we run into this a lot. We have people that are using 5 gigahertz in an office environment where people are bringing their own device. Because what happens is some of those bring your own device, some of those inexpensive Android phones, etc., don't support DFS channels. So what happens is you end up with some of your users complaining they can't get on the Wi-Fi, they can't even see the Wi-Fi, and that's the reason, is because your access point is using one of those DFS channels that client device can't even talk to. In addition to dealing with the fact that depending on where you're physically located, those channels might just shut off randomly at different times. Mike's asking about 802.11ax, so we'll talk a little bit more about that later. So again, going back to increasing speed, one of the ways we increase speed is by increasing the amount of bandwidth that's being used. So if we go from 20 megahertz channels to 40 megahertz channels, you now go from 26 non-overlapping channels. So you've reduced it down to, what is that, 12, 15? But if you want to avoid DFS channels, which you often do, you're now down to just 4 channels that you can use before you start getting interference. So as soon as you get to 5 access points, you've now got interference issues, whether those are your network or whether those include your neighbors, people on different floors, etc. So 802.11ac increases speed also by allowing you to use 80 megahertz channels. So now you're in a situation where you've only got 2 channels that can be used before you start causing interference between your access points. And if you really want to maximize your performance and get the best speed that's advertised on all those 811ac devices, you got to jump up to 160 megahertz channels. And now you absolutely have to use those DFS channels. So if you're using an access point in an area where there may be weather radar in use, you cannot use 160 megahertz channels at all. So some stuff to keep in mind there when it comes to maximizing speed and channel selection. The other thing I was talking about before for increasing speed is using spatial streams. So one of the things we talked about before was that RF signals, just like sound waves, bounce off of different surfaces and can create echoes. So, we send a bit of signal out. It can take different paths to get to the other side. It can take a direct path. You can also get the sound, or the RF in this case, bouncing off of walls and getting there a little bit later or a little bit different times, so you create an echo effect. So that had been a problem, especially with 802.11b, G, and A. Where that thing is what we call multipath. So the same data is taking multiple paths to get there, and it creates this echo effect that makes it hard for the client device to understand the signal that was being transmitted to it. So somewhere along the lines in 802.11 and really with 802.11ac, we realized, well, we know how far apart the different antennas are in our access point. So what we can do is we can take advantage of this echo effect or this multipath effect, and we can use that to send different data using different spatial streams. So the spatial stream is essentially a different path. So we know that this antenna, we can send data here and it'll take, 1 millisecond to get there. Where if we send it through this other antenna, it's going to bounce off of a wall. It might take 1.2 milliseconds to get to the other end. So with some fancy tricks and stuff with the signal processing, we're able to send different amounts of data over these different paths. So the most common way of doing this is by combining the data together. So you'll send in the case you've got, say, 2 antennas, one antenna will send 150 megabits per second of data. The other antenna will send a different 150 megabits per second of data, and those combine together to create a 300 megabits total data that you can send simultaneously down the road. Now, with 802.11 AC, with Wave 2, we did some other tricks with it. So we can also use these multiple streams or the multiple paths to send data to different devices. So instead of sending 250 megabit streams to one device, we can send 2 separate 150 megabit streams to 2 different devices. So you're still sending 350 megabits of data, but you're sending now 150 megabits to one client, a different 150 megabits to another client. So we call this MIMO, or specifically downstream or download MIMO, allowing the access point to send data to 2 client devices at the same time, which is great because oftentimes client devices aren't able to support the maximum number of spatial streams that the access point can. So it allows you to reduce airtime utilization by sending data to multiple clients at the same time. So when you're looking at spec sheets for most business class APs, you will see them defined as 2x2 or 3x3 or 4x4. So the first number is telling you basically how many different transmit spatial streams you have. The second number is telling you how many different spatial streams you can listen to at the same time. So 3x3 is 3 spatial streams, 2x2 is 2 spatial streams. You will occasionally run into some things where you might see 3x2. So the access point or your client device can send 3 spatial streams at the same time, but it can only listen to 2 spatial streams back, and that'll affect your speed in different directions. You'll also see occasionally, most commonly on Cisco equipment, you'll see a number such as 4x4, then you'll see a colon with a smaller number after it, so 4x4 colon 3. So even though you've got, what they're basically saying is, hey, we have 4 different antennas, we can have 4 different spatial streams, the colon number is telling you how many of those spatial streams you can actually use realistically at a time. So even though it says 4x4, realistically you're only at maximum still using 3 spatial streams. It may give you a minor boost in receive sensitivity because the access point can switch which 3 spatial streams it's listening to at a time, but realistically it doesn't make that much difference. It's more of a marketing gimmick. So to combine all of that together, this little chart is showing you the differences in speed that you can achieve based on how many spatial streams you've got, 1 through 3 in this example, what type of modulation or encoding you're doing, 16, 64, 256-bit QAM, and then how wide of RF channels you're using. So you can see here, if you're using 1 spatial stream on a 5 gigahertz radio using 256 QAM and 160 megahertz of channel, you can get a maximum data rate of 866. But if you don't want to use DFS, we know we can't use these 160 megahertz channels. You can only use an 80 megahertz channel. So you can see the speed is reduced down to 433. It's essentially cut in half. If you want to do this on a 2.4 gigahertz radio, you're limited to 64 QAM and a 40 megahertz channel. So your max data rate is only going to be 150 megabits. So it gives you an idea here of how those 3 different things, when you combine them together in different ways, give you the different data rates that you're able to achieve using Wi-Fi. So another common question you get is, well, how many devices can I fit on one access point? So in the real world, generally your access point is not the limiting factor. And we'll run into this a lot. Well, this data sheet says this device can support 512 clients or 256 clients. When you see that on a data sheet, that's telling you basically how much memory is available to keep track of different clients, which makes sense. The problem is when it comes to real world, how many clients you're actually going to be able to get on the access point, it's almost entirely going to be limited by the 802.11 protocol itself and the types of data and clients you have on that access point. So generally, you're going to max out the number of clients well before you get to whatever the hard limit is that's on the data sheet for the access point. As we talked about before, there's no management or organization of which client device gets to broadcast at a time. And if more than one tries to broadcast at a time, you end up with interference and those packets for both clients being dropped and needing to be sent again later. So that's where you tend to run into your limitations, is just how the 802.11 works. So, you know, are the client devices using three spatial streams? Are they using one spatial stream? That will affect things. Are they doing video streaming? Are they trying to do VoIP? That will affect things. VoIP is really sensitive to packet loss and jitter. So if you're trying to do voice over Wi-Fi, you actually can support a smaller number of clients before you start having users complaining about voice quality issues than, say, if you're streaming YouTube. Even though YouTube uses a lot more bandwidth and is sending continuous data, you're able to buffer and do some other things there, which means users aren't going to complain as quickly as they would if they were doing VoIP, which uses almost no bandwidth. So we've got an example here using a couple different simulated environments. So in this simulated environment, each three situations, we've got client devices that are transmitting a stream or receiving a stream of 3 megabits per second. So what you can see is if you're using high-end laptops that support 3 spatial streams on an access point that supports 3 spatial streams, you're going to be able to fit 34 laptops on there before you start seeing any degradation of that 3 megabit stream. So you'll have 34 devices all handling a 3 megabit stream, no problem, for a total combined 100 megabits aggregated bandwidth. But if we go to, say, a tablet device, which only supports 2 spatial streams, we suddenly see that we've dropped the number of client devices down to 21 that can work on that network and handle a 3 megabit stream, just because they're not as effectively utilizing the available spatial streams that are there in the airtime. So your overall aggregated bandwidth drops to 65 megabits per second just by switching from a device that supports 3 spatial streams to 2 spatial streams. Same thing, if we drop to a typical inexpensive phone that only supports 1 spatial stream, well, now we can only fit 10 devices on there that are still sending or receiving a 3 megabit stream, and the overall aggregated bandwidth is 30 megabits per second. So you can see in the real world situation where you've got a mix of different types of devices that are all trying to use there, you can have dramatic differences in how many devices you can get on that access point before your users are going to start complaining. So moving on from that, you know, we run into something here called co-channel interference. So co-channel interference is what happens when you have 2 or more devices operating on the same channel. So, you know, we talked about before the hidden node problem, just the issue where if you get a lot of clients on an access point, 2 or more can decide to transmit at the same time. Those signals basically cancel each other out and the data is lost. We were also talking about before about channel usage and where you start getting interference between access points because they're operating on overlapping channels. So that is what is co-channel interference. So in a traditional access point scenario, the coverage that you get from your ceiling mount access point is an umbrella shape. It's a circle, radiates outward. So as you see in this situation here, if both of these access points are operating on an overlapping channel, there's not really a lot of interference except for this little area here where client devices in this area may get interference from each side. So how do you reduce that interference? So the traditional way of doing that is by reducing output power, right? As we talked about before, there's a lot of, you know, there's usually a huge difference in the output power of your access point versus the client device. So traditionally, the way you tried to reduce interference between access points was by reducing the power. that absolutely works, is very helpful at reducing interference between access points. The problem is it lowers your signal-to-noise ratio. So you get less packet drops from interference, but your client devices are operating at a lower data rate. So since they're operating on a lower data rate, you hurt your overall aggregated bandwidth. So just again to show here, the solution to that is something we call smart antenna. So again, traditional access points you mount up on a ceiling are doing sort of a circular coverage area. We also have something called directional access points, which are most commonly used outdoors, where they focus the signal in a certain direction. So what smart antenna does is it uses a special type of antenna that has hundreds and hundreds of different antenna patterns. And what it does is on a per client basis, it goes through hundreds of different antenna patterns and chooses the antenna pattern that both maximizes signal coverage towards where that client device is, and also minimizes coverage on the receive side of things from where other interference might be coming from, whether that's microwaves, whether that's industrial appliances that are putting out RF interference, whether it's other access points or other wireless devices. And it really works really nice. The client does not require anything special, unlike beamforming, and it can also work even when the client is moving, unlike beamforming, which really works best when a client device is stationary. So we're going to give some real-world examples here. So this is a hotel environment. This works also, though, for large homes or for an office environment. So we're using 5 gigahertz radios, and we've got multiple access points spread out. We can see the channel that each one of them is using. So we've got a 48 megahertz, an access point using channel 48, another access point using channel 48, et cetera, et cetera. We've got one here that's using channel 100, and then on a different floor, directly above or below that, we've got one over here using channel 100, one over here using channel 100, et cetera. So what we've done here is we've taken 2 very similar devices. We've taken our hospitality AP, the NWA1302, which does have smart antenna, and we've taken a Ubiquiti UAP AC -IW. So both of these have similar output power. Both of these have similar form factors. Both of them support 2x2 802.11 AC. So what we see is when we've got one access point operating, speed is very comparable. Ubiquiti beats us by a little bit. 406 megabits per second aggregated bandwidth versus 404. And channel usage or channel efficiency is about the same at 67%. So the next thing we do is we turn on one of the second access points. It's not right next door, it's a couple rooms down, but there is still going to be some interference even though you've got physical separation between the devices. So what happens here is really interesting. You'll see here that the aggregated throughput goes up for both sides. Ubiquiti goes up to 555 megabits per second aggregated throughput between both access points. But you will notice the Zyxel aggregated throughput jumps up to 785 megabits per second. And that has to do with the smart antenna being able to change antenna patterns, eliminating that co-channel interference, allowing devices on both access points to operate at the same time without interference. Something else you'll notice also because of the smart antenna, there's not much speed difference between both access points. It's pretty equally distributed between both access points, where if you look over here at Ubiquiti, you'll see that one access point is getting double the aggregated bandwidth from the other one. And then when you look at channel efficiency, we're able to actually exceed 100% channel efficiency because we're spreading it out over a larger geographical area, and the smart antenna is allowing that channel to be used simultaneously in 2 different locations, where without smart antenna, you're maxing out at 95% of the theoretical channel utilization. So now we'll jump up and have 3 access points operating. Again, they're not next to each other. There is physical separation between these, but you get co-channel interference over a surprisingly long distance. So again, what we see here is we've increased the overall throughput. And again, you'll notice the aggregated throughput for each access point is evenly distributed. Where with ubiquity, you run into a situation where you really start seeing some really significant differences in which access point gets its own allocation of the available bandwidth. And again, we actually see here is that the channel utilization actually goes down just because of the interference issues, where our channel efficiency continues to go up because we're allowing these three access points to simultaneously use the same bandwidth. But because of the smart antenna, we're able to ignore the interference that would be caused with a normal access point. Okay, so now we'll start talking about some of the other things we run into here. I'll start talking about installations. So your traditional circular access point with no physical external antennas is optimized, as we talked about before, to have sort of an umbrella-shaped pattern. It's designed to be mounted on a roof and then provide a big circle of coverage to it. Unfortunately, as you've probably run into out in the field, you don't always get to mount stuff on the ceiling for various reasons. Oftentimes, you're forced to mount that access point on a wall. The problem with that, as we see over here, is you end up shooting a bunch of your signal up into the roof and into the floor. And it's either being wasted there or it's causing interference on those other floors, and you don't get good signal penetration over here. So smart antenna can help solve that by changing the antenna pattern that it's using based on the physical environment. The other thing we have is we have something in some of our access points called dual optimized antenna. So instead of having a single set of antennas inside the device that are optimized for the ceiling, we've got two different sets of antennas. One that's optimized for ceiling mount and one that's optimized for wall mount. And we let you switch between those based on where you've installed the device to maximize your coverage. So some other things here is a general rule, when you're mounting a ceiling mount access point, you want to mount it on the ceiling. And within reason, you want to mount it at the highest point possible. What you're trying to do is minimize the difference or minimize the signal distance between your client devices and that access point. And you're trying to minimize the obstruction. If the access point is mounted down lower, a lot of those client devices are having, in this situation here, to send their signal through the cubicle walls, which will attenuate the signal. So by mounting it higher, you allow the signal to go over the top of those cubicle walls, and you get better coverage. So one thing that people do a lot, or that you don't realize that you can do, is that in a traditional office environment, right, you've got a drop ceiling. So the actual physical ceiling is up here, and then you've got a drop ceiling that's, you know, maybe 10 or 12 feet above the floor, where you've got little acoustic panels. Those acoustic panels don't cause a lot of attenuation. So we see a lot of people worrying about, well, how do I mount the access point to the drop ceiling? I don't want, you know, my customer doesn't want us to poke holes in the drop ceiling to run the Ethernet out. They don't want us physically mounting them to the drop ceiling, and in some cases it may be against building code to have something physically mounted to the drop ceiling. Just set them on top of the drop ceiling. The drop ceiling isn't going to cause that much attenuation of the signal. Generally, you don't want to mount them up here on the physical ceiling because you've got ductwork, wiring, and other stuff up there which are going to interfere with the signal. So oftentimes the easiest way to mount something is literally just to rest it on top of the drop ceiling. Can't be seen from down below. It's not going to, the drop ceiling is not going to cause a lot of attenuation. You don't have to worry about physically mounting it to something and holding it in place and drilling holes. It works really well. When we're talking about hotels, the traditional way to do it is to use umbrella coverage, which is you mount access points in a common shared hallway. And one access point provides coverage from anywhere from 4 to 8 rooms. What we're seeing, at first, the trend started in high-end hotels, but we're seeing it now in your traditional mid-tier business hotels, you know, your Holiday Inns, your Hampton Inns, you know, Fairfield Inns, things like that, is a move away from umbrella coverage and a move towards putting an access point in each individual room or every other room. And this is just because people are using their Wi-Fi in hotels. They're using much more bandwidth intensive applications than they used to, specifically Netflix and YouTube, trying to stream HD video to their laptop. And you find situations where people just have a lot more Wi-Fi devices than they used to. You know, it used to be back in the day, you had a laptop, and it was maybe you had a laptop and a phone, and now maybe you've got a laptop, a phone, a tablet, plus your spouse or whoever you're traveling with also has, you know, multiple devices. So umbrella coverage just doesn't provide the bandwidth to handle that, and just has too much RF interference when you get a lot of devices on one access point. So again, you see a lot of people moving towards one AP per hotel room or per every other hotel room, mounting them in the hotel room itself to help deal with degradation from the signal going through the walls. So what you want to look for in these situations is you do want something that's got a locking mounting bracket, because people will steal the access points out of a guest room. Another thing to look at feature-wise is the ability to disable the LED lights, because no one wants to try to go to sleep when there's a green blinking light above their head that's flashing all night long. When we come to public areas, whether we're talking lobbies or restaurants or conference rooms, generally what you want to do is you want to cover each physical area separately. You don't want to try to bridge, say, the restaurant to the lobby or vice versa. And the number of APs you want to have in there is going to have to do with the user density you're going to have in that area. You know, if your lobby has a lot of business users, has a lot of chairs and tables that people might be hanging out on, you might want more access points to handle that. You want to use load balancing and client steering to help distribute the users across the access points and help make sure the clients are being steered to the appropriate access point for where they're located at. Smart antennas make a huge difference, especially in conference rooms and things like that, where you've got a high density of users. For schools, when you're doing your deployments there, a big question to ask is a smart classroom, what are they using the Wi-Fi for? If they're simply using the Wi-Fi for students to browse, say, Wikipedia or send emails or something, one AP per classroom is probably enough. But if you're dealing with a smart classroom scenario where the teachers are sharing their whiteboard and projecting that onto, let's back up, where each student has their own Chromebook or their own tablet and the teacher is streaming the whiteboard directly to those displays or is streaming video simultaneously to all 20 or 30 or 40 students, one access point per room isn't going to cut it. You're going to want to have at least 2 access points per room. Both Nebula and our controller managed access points have a special smart classroom mode specifically designed for the rigors of a classroom where you will have 30 or 40 devices coming online simultaneously and all requiring simultaneous video to be streamed to them or other data to be streamed to them. So those are things to take into account. Also, you don't want your teachers and your students on the same network, so you're going to want them on different SSIDs, and you're going to want those separated by VLANs. And if you've got 30 or more students in a room that are all going to be online at the same time, you do want smart antenna on your access points. So now we can start talking about 802.11ax, which is what Mike's kind of been asking about here. So let's talk briefly about it. It's the new 802.11 standard, so this is what's going to replace AC as the latest and greatest. You'll also see it called high efficiency wireless or Wi-Fi 6, which is what the Wi-Fi group is branding it as. You'll probably see Wi-Fi 6 used more often on consumer equipment and 802.11ax on business equipment, but it doesn't really matter. It's all talking about the same thing. So unlike 11AC, a lot of the new improvements in 802.11ax will work on both the 2.4 and the 5 gigahertz radio. So with 11AC, you only saw improvements on the 5 gigahertz radio. So now you will see improvements across both. And with 802.11ax, we've essentially fixed all of the problems that we talked about in the earlier slides today with 802.11. They have done all sorts of new technology that we won't get into today. They've increased the QAM from 256 to 1024. They've added both upstream and downstream OFDMA. They've done some stuff there called BSS color coding, spatial frequency reuse, all of these things that are designed to solve the biggest issues we have with Wi-Fi. It reduces the interference between access points, even when those access points are on different networks. It reduces latency. It reduces interference between client devices. It allows multiple devices to broadcast at the same time. 802.11ax is fantastic if you're doing voice over Wi-Fi. It'll let you get a lot more devices on one access point. It will solve all those issues of people complaining about poor call quality on VoIP. It'll be great in convention centers and warehouses and things where you've got a really dense environment. It'll be great in office buildings where you've got multiple offices and you only can manage, your office and you have no impact on the other offices. It's going to be great and fantastic going forward. So there's some things to keep in mind here. One is the IEEE working groups. This is the group that's making the raw official standard that defines everything, isn't expected to have final approval until a year from now, a year and a month from now. And it keeps slipping. The work group approval was originally scheduled to be done. The draft approval was scheduled to be ready in January of 2020. It's been delayed now to September of 2020. I would not be surprised at all to see the official spec delayed approval until 2021. Now, that hasn't stopped people from shipping product that they're calling Wi-Fi 6 or 11ax. We have seen a bunch of that product launched last year. And then to confuse things even more, the Wi-Fi Alliance is offering Wi-Fi 6 certification. They just started offering it a few weeks ago, at the end of September, I believe it was. So how is all that possible? The short answer is some of the stuff that's come out that's calling itself Wi-Fi 6 isn't. Just like AT&T rebranded their LTE as 5G with a little E after it to try to make people think it was 5G. It's the same sort of thing there. Because there is no standards group or marketing group that enforces what you call Wi-Fi 6. So short version, though, is that we're up to draft 5 of IEEE 11ax, and while they're still hashing out the details, the core of what's needed to implement Wi-Fi 6 is now out there, and that's why the Wi-Fi group is able to offer Wi-Fi 6 certification for compatibility with what's out there. So let's go. Why is it not working here? There we go. So some things to keep in mind is, like I said, a lot of that first-gen stuff out there doesn't actually support everything which makes Wi-Fi 6 Wi-Fi 6. So this example here, I'm talking about the Qualcomm Gen 1 product and the Qualcomm Gen 2 product. Qualcomm Gen 2 just started shipping, so any access point that was available in June, July, August, or before that is pretty much guaranteed to be using the Gen 1 chipset. So that means OFDMA is only going to work in the downstream. It's not going to allow multiple clients to broadcast back to the access point. That's going to be really important, especially for doing VoIP. Upstream MIMO, not supported in that Gen 1 chipset. TWT and BSS coloring, really important when it comes to latency and being able to solve the code channel interference issues. Not available on that Gen 1 chipset, and you're not going to be able to upgrade it to be fully compatible. Similar things with Broadcom. I don't have a breakdown of the different Broadcom generations, but it's the same sort of thing. Broadcom beat Qualcomm by a month or two to shipping chips that's in theory will support the full Wi-Fi 6 standard, but the same sort of thing. If you're looking at a product that's been on the market for a while, chances are it's Gen 1, and the important features that make you want to have Wi-Fi 6 aren't there. So you may have noticed today we put out a press release launching or announcing a new product, the WAX650S. So that is our new 802.11ax access point. It is one of 5 that we are going to be launching in the next few months. We will have a dedicated training on that later on down the road. But it is using the Qualcomm Gen 2 chipset. So the good news for you there is all of the standard features for Wi-Fi 6 either are currently supported by the silicon and will be supported at some point via a free firmware upgrade. Some of these features, it's still kind of rough, or the support just isn't there from the chipset vendor, or we're still waiting for more of the details on the official 802.11ax draft to be hashed out before we can roll those features out. So the new product, the new access point, we are currently looking for partners who are willing to help us beta test the WAX650S. So if you're interested in testing it, you've got some use case scenarios that will benefit from Wi-Fi 6, and you have the time to actually test it, reach out to your salesperson and they can put you on the list. We'll probably start shipping out some of those evaluation units when we come back from the Thanksgiving break. And the WAC will be available broadly to all partners probably in January. That's what we're currently shooting for. As always, a lot of this depends how the beta test goes, and a lot of this is dependent on Qualcomm and the quality of drivers and feature support that Qualcomm is rolling out. The full set of Wi-Fi 6 features probably won't be available until the end of Q2 or the beginning of Q3 next year. And that's going to be true no matter which vendor's product you buy, because the limitation right now is a combination of chipset support or chipset software support, and in some cases, the fact that they're still hashing out some of the details in the draft spec. So those need to be hashed out before you can actually roll it out and know it's going to work. So just keep those things in mind. But otherwise, that is the end of today's presentation. I hope you learned something. I know the material is kind of dry and kind of technical, but I hope you were able to pick up enough out of that it helps you understand a little bit better what's going on with Wi-Fi, and maybe helps you understand some of the issues that you've come across out in the field, and that maybe gives you some ideas of maybe how to solve some of those issues. I do want to bring up here, just as a reminder for everybody, that we have a user forum, forum.zyxel.com, where you can get support from each other. But this forum is also monitored by our R&D team in Taiwan. So if you post something today, asking a question, there's a good chance you will get an answer from an RF or R&D engineer overnight when they're back in the office in Taiwan. They do check it almost every day, and they do respond on there. So if you don't have an urgent question, it's a good place to go to get support. Of course, as always, if you need quicker support, call in to our 800 number, and you can talk to somebody here in our Anaheim office. Again, if you have questions, you can use the Q&A box to type them up and send them to me. I don't have any currently. And my email is there on the bottom of the screen, so if you want to give me some feedback, ask some questions that require you to type up maybe a little bit more than you've got time for here, you can email me directly with those questions. I will do my best to answer them for you. But otherwise, I would just like to thank you for turning out today. Some future stuff coming up. We've got a Nebula webinar this Thursday. We will be having a dedicated Wi-Fi 6 webinar in the near future where we talk a little bit more detail on some of those new features that are part of Wi-Fi 6 and make Wi-Fi 6 so interesting. So that'll be coming in the near future. And we will have a WAX650S dedicated webinar probably in January. I don't think we'll do one now just because of the limited availability. But those are all coming, and then Troy, of course, has some other webinars that he's coming up here. But, you know, something we need from you guys is we need your suggestions as to what you would like these webinars to be going forward. We want these webinars to be valuable for you. So we need your ideas of what you would find valuable. Do you want a webinar where we tell you how to configure Nebula for VoIP? Do you want a webinar where we tell you how to configure content filtering on a USG? You know, what sort of stuff, what sort of trainings, what sort of information would you like us to provide in these webinars to make them more valuable for you, to help you sell the product, to help you more quickly and efficiently install and set up the product? Email us, let us know, so we can start putting those together, because we absolutely do want to see those suggestions so we can put them together for you. I'm not seeing any other questions coming in. Thank you guys for the comments. I see the comments, but no other questions. So I am going to go ahead and end today's webinar. So if you're typing something up that's a question, quickly highlight it, copy it, and then paste it into an email to me, or send it to Jake or Ivan or Sandra or Jeff, whoever you normally talk to, and they can forward it to me if you haven't got my email yet. But again, thank you guys for turning out. Hope you learned something, and thank you.